Guten Abend, willkommen Damen und Herren zu meinem Vortrag über LLM Inference on device in React Native, the practical aspects. And now we will switch to English. So welcome everyone. I'm very happy to join you on the scene here at the React Universe meetup with Zalando. And yeah, I think we can move on. So first, maybe a few words about myself. My name is Artur Morys-Magiera. I work as a senior React Native engineer at Callstack. And apart from this, I'm also pursuing a PhD degree at AGH University in Krakow. I would like to divide my talk today into three primary sections. Each will be a question and each will start with W, and each will be, which will have at least one word in German. So the first one will be Warum? Why even run LLMs on device? The second will be Was ist wichtig? So what matters, and firstly to the user, from the user's perspective, then welche libraries, which libraries are available to achieve the goals we want to. And the last one will be Was ist wichtig 2, what matters to the developer, so from the developer's perspective. Before we dive into the first block, let me quickly summarize the scope of our considerations, because nowadays, people, and recently even for years, people often say AI. And by saying AI, they actually usually mean LLMs, which is just a subset of the whole thing. Because in reality, LLMs are a subset of deep learning, which itself is a subset of machine learning. Deep learning includes other methods, for instance, convolutional neural networks for image processing or recurrent neural networks for time series. Their tasks are like classification, regression, etc. Machine learning itself also includes other methods. This is clustering, this is gradient boosters, support vector machines, logistic regression. There's a whole bunch of those. And all of those methods fall into the category of artificial intelligence. And today's talk will only touch LLMs. So we'll only stay in this one specific subset that's currently very popular. And yes, we will talk about a few libraries, a few techniques, a few topics. They will touch LLMs, but some of them will also allow us to run other deep learning models, not only LLMs. And let's begin with the first question. So why even bother with running LLMs on device? What's the purpose of this? And the answer is, the first reason is for reliability. We may want the offline experience, so that our model runs regardless of whether the server provider of our model is available, regardless of the state of the network for the user, whether it's fast, whether it's even available or not. And the second reason, which is privacy, is partly implied by the first one, because if we hermetically process all the data inside the device, it never leaves it. We don't send it over the network, so we don't get the implications of actually dealing with a third-party service provider that runs the inference and processes, at least for some time, the data, then we send them. And also, we don't actually send the data even through the network, so we don't need to worry about this layer of security. And the third thing is latency. So as you can see in the effect, the user won't be kept waiting until the inference provider, such as any cloud provider, needs to, the request needs to wait in the queue until the server actually has time to run inference for this particular request, which is important because at high traffic times, or maybe if the provider is having some downtime or they are doing an upgrade, it may become a problem. And now I think it's time to discuss the needs from the user's perspective. So firstly, the model size, because a typical non-technical user, which is probably the typical user persona for a whole bunch of applications, does not usually know the technical side of the application, and they usually don't want to know it. They don't want to know how it works. They just want it to work well. So they won't be interested in noticing that the application actually downloads a model that weighs a few gigabytes of space, such as, for instance, Llama, which weighs about 5 to 6 gigabytes in the unquantized base version. So if your application targets this user persona, it's very likely that they will soon run out of memory, because if you build a few different applications that do so, each of them will download a separate copy of model, even if it's the same model. And the user will end up with a whole bunch of memory on their device being consumed by that. And this is undesirable for them. However, there is also the other approach. There are libraries that offer models provisioned by the OS, for instance, Apple Foundation models that are provided by Apple Intelligence. And in this case, the models are provisioned within the OS. They are optimized, they are shared. So, the OS comes packed with them either way. You don't need to download them. They don't take the disk space. They are just there and you can use them. So this is one solution for this. There is also another aspect, which is performance. And it consists of a few things: the throughput, resource usage, and initial latency. So the resource usage and throughput usually primarily depend on the runtime that backs the inference. This is usually the transformer block that performs most of the work. And since modern devices are equipped, apart from the CPU, of course, usually with a GPU and sometimes even with an NPU, which we will talk about in a second, we can apply acceleration, hardware acceleration for those computations. So GPUs typically have thousands of cores compared to tens of cores in the case of CPU, the central processing unit. Parallelization would be a key improvement here. And fortunately, pretty much all the operations that we are performing in deep learning includes matrix operations, and these are easily parallelizable. We can parallelize a whole lot of these computations. And thanks to this, we can take advantage of the GPUs that devices have. Similarly, if they are equipped with NPUs, neural processing units, which are even more specialized hardware devices that have hardware accelerated flows for some of the mathematical operations that are some of the data structures, this can optimize it even further. The problem is there is a large fragmentation on the market. So there is a bunch of vendors that actually produce a bunch of lines of the devices, and each of them may provide a different SDK, for instance, to code this. So it's undesirable for developers to maintain end implementations of this, and that's why it's problematic. On the other hand, there are solutions like OpenCL, which is a library for computations that run on accelerated systems, on other units, that actually abstract it away. So you write only one implementation using this abstraction, and it's the matter of OpenCL to worry about this. Most of the vendors, for instance, it's ARM that has Mali chips, it's PowerVR, it's, for instance, Adreno. All of those chips have support for OpenCL. Basically, the manufacturers need to provide a driver. So they do support it, which partly solves the problem. But on the other hand, this library may have some drawbacks. For instance, with the abstraction that helps you, comes also the invisibility. So if you encounter a performance problem, it might be hard to actually debug it, to know what to change, how to fix it. And we actually have a case study about that, because with one of the LLM runtime frameworks that we are using, we utilized llama 3.2, 3 billion parameters. As the model would be loaded, the underlying procedures would look like the above when traced. So we could see the initialization and prefill phase, which would be good. It would take about a second, maybe something less, which is acceptable for the users. This is the cold start, we could call it. And then all the other parts of the inference, so the first token, which we can see in the next blue and yellow boxes, and finally subsequent token generations, which take much faster because of caching. So this is acceptable. This is how it should look like. However, we encountered a case when the plot looked like this. And this is for 37 seconds being taken by the prefill and initialization phase, which is totally undesirable. And the final reason that we were able to track down, because this happened on the MLC LLM library, which stands for Machine Learning Compiler, you might have or not heard about it. We tracked this down with the help of the maintainers, and we're able to find out that actually the kernel, which is a subprogram that runs on the GPU because it was all accelerated, would be inefficient basically on only some of the devices that included a specific GPU chip. And that's not a bug in the code. It was just because OpenCL, which was the backend used here, was doing suboptimal operations. And the solution was simple because MLC provided support for 2 formats of models. The only difference between them was the layout of memory. So basically, one included a matrix of weights and the other included a transposed matrix of weights. So rows swapped with columns. That's it. And basically, the functions that were doing a transpose operation were inefficient. And that's exactly the root cause. If we change the format, it was all good, like on the first plot. This is exactly the same model on those 2 plots. So this is one lesson learned here. When it works with such a layer of abstraction. But when it doesn't, systems of such complexity are very hard to actually trace down and debug. And now let's move forward. So even if our model achieves great performance, we need to remember about the wider target audience. Because even if it runs well on our flagship devices, it may run worse on other devices. The devices usually have a GPU, sometimes even an NPU. And normally you would need to, maintain a code base for all of them. Apple devices, for instance, support Core ML since iOS 11. However, it's important to keep in mind that older devices of Apple, although the code will run there, will just run slower. And on Android, it's even a bit more complicated. There's a fragmentation of the chip manufacturers that I spoke about. And also there are NPUs which have different SDKs. So usually it's undesirable to write all of this code. And that's why usually you will want to pick a library. And we will also cover the choice of libraries in this talk. So moving on to the selection actually of libraries, before we delve into it, I would like to very quickly, briefly summarize how an LLM actually works. Because we have many libraries that actually do inference on models, not only LLMs, but also others. And it turns out that it's not enough for LLMs, because typically we have a prompt, which is just a string, for instance, hello Berlin meetup. Then we need to tokenize it. So this is performed by a piece of code that is called the tokenizer. So here we split the prompt into smaller chunks, and these chunks may not necessarily be full words. So it's up to the tokenizer to do it. The tokenizer is deterministic. And then we generate embeddings. So these are the numbers that you can see there. Each of the tokens can be mapped to an embedding. And such vectors, because each embedded token is a vector, up to a selected metric, should be in this n-dimensional space close to each other, provided that these words have a semantically similar meaning. And then when we put them through the transformer, which does the majority of the computational cost here, we obtain logits, which are raw, unnormalized numeric values assigned to tokens that can be outputted by the transformer. And we need to apply first the normalization and then sampling to actually be able to predict the next token. When we get the next token, we can detokenize it, of course, to obtain a string, and then concatenate it with the prompt, because LLMs are autoregressive models, and run the LLM again on the concatenated prompt with the new token. And that's how they generate the text. You can easily see it when you, for instance, stream some response, and you can see the cursor moving, new letters or actually tokens, so pieces of words usually appear. And you can then run the model again. And there is also an optimization here, because firstly, you can pre-allocate the buffers and reuse them. That's natural. And also because part of the prompt was already processed, you can also use a KV cache to actually store some of the intermediate results of your computations on the tokens that were already processed. And now we can actually move on to selecting the libraries, having all those considerations in mind. The first one that I would like to cover is React Native Fast TF Lite. So this is a library that supports iOS and Android. And maybe even before I speak about that, let's also ask ourselves a question. So is there one library to rule them all before we start? The answer is no. The choice depends on your use case. And we will cover all of the details that we were speaking about from the user's perspective, as well as the problems from the technical side right now. So this library supports iOS and Android. The models that are supported here is, the format is called TF Lite. It has been renamed by Google to Lite RT. So this is the new name. The models are stored on device, so you can either distribute them with your app if they are probably very small, or you can store them on a server. The app can fetch them, store them in some kind of app data directory, and then load them, use them for the user. This library has hardware acceleration support. It has support for CoreML, Metal, which is the accelerator for Apple platforms, OpenCL, so this is the abstraction layer that I talked about that supports a wide variety of GPUs. OpenGL, so yeah, 3D graphics API, you probably know it, and an API which stands for Neural Network APIs for Android. So this is a library for Android that allows you to do some computations for neural networks, and of course on the CPU if the device is not capable of them. Here the technologies are actually mixed because CoreML and Metal are for iOS. OpenGL, I believe, was also. OpenCL is officially supported on most of the GPUs for Android, but officially not supported by iOS. And an API is Android only. Another library is ONNX Runtime React Native. So this is a wrapper of ONNX Runtime. Official wrapper that is a low-level library called ONNX, which is meant to be a runtime for machine learning. It supports a wide variety of execution providers, that is QNN, which is Qualcomm's API for neural networks, and an API for Android, CoreML, XNNPAC, which is a very optimized, powerful toolchain for linear algebra and computations. ARM, the standard for CPUs, also has another SDK for this, and TVM, which is Apache TVM, which is a framework for accelerated computing in machine learning, and finally, of course, the CPU. And for CPU, I believe it was also tweaked for Neon CPUs. This library, however, has some drawbacks. On the other hand, apart from transformers, of course, it also supports all other architectures of neural networks, but it lacks all the instrumentation that we spoke about on the chart. So there is no tokenizer, there is no sampler. All of this is missing. You can only run the transform itself. You need to also embed the tokens. So likely you either have to implement this or use a ready library. For instance, Hugging Face provides provides transformers library that you can use. There is also a library named React Native Transformers, which is open source, and it used to wrap both this library and the Hugging Face Transformers library, actually, completing the image of this this solution to fully support, let's say, LLMs, if we can say so. And of course, which is something I haven't mentioned, all of the libraries that we mentioned, each of them has a different API. That's probably, you could have expected that. There's also React Native ExecuTorch, which is a wrapper for ExecuTorch. That is a runtime for both just deep learning models and LLMs. It supports the Torch PTE model format. It optimizes the model at compilation time, similarly to the TVM backend. Torch has a feature that it actually generates a different separate file for each of the supported backends. And the range of supported backends is pretty wide. It's XNNPAC, it's CoreML, MPS, which is Metal Performance Traders. For Android, it's Vulkan and Qualcomm's library. The support is a bit limited. It's React Native 081 plus and above, iOS 17 and above, and Android 13 and above. The API, again, is custom. And now we can move on to, let's say, ecosystem of a few libraries that are interchangeable or can even play together. That's called React Native AI, and we are actually building that. It bridges almost all the available LLMs, soon others, and machine learning as well, runtimes, under one familiar API you may know from Vercel's AI SDK. So let's take a look at React Native AI/Apple at first. We have platform support only for iOS, which is natural because this library depends on Apple Intelligence, which is iOS only. It allows you to run the Apple Foundation models only, again. These models are shipped with OS, which is the key difference between this library and all the former ones, because with the former ones, you need to take into account that you need to grab at least 3-5 gigabytes of the user's memory. Here you don't. The device support is iOS 26 plus for text generation and transcription, and for speech iOS 13 plus. And the other difference here is the API, because this library has compatibility with the Versal AI SDK, which you may have already known. The limitations are also there because, for instance, you cannot put, of course, a custom model, which I already mentioned. Apart from this, you also need to remember that Apple has also set some fixed models. So they, for instance, have a set context window size of 4096 tokens. And you cannot exceed that, otherwise you will get an exception you can catch. And, translating this from the technical language to human readable, Apple has estimated in the documentation that a Latin character takes about 1/3 of a token, which means that actually you have 3 times the 4096 tokens as the maximum prompt length with Latin characters. If you use multi-byte characters such as Chinese or Korean, then it's 1-to-1, so 4096 multi-byte tokens. The next library is React Native AI/MLC. And this is a wrapper that supports both iOS and Android. It's a wrapper for the MLC LLM project that I have already mentioned. MLC stands for Machine Learning Compiler. This engine is based, again, on the Apache TVM project that I already mentioned in case of ONNX. Hardware acceleration here is done through OpenCL, Vulkan, or CPU, which is optimized for Neon CPUs as well, I think. And MLC also applies various very complex optimizations during compilation time. For instance, operator fusing, which is converting a sequence of mathematical operations into an equivalent but simpler, computationally cheaper alternative, as well as some others. The models need to be, of course, stored on device. So this is a library that would be very similar to the first ones that we mentioned in this particular matter. And also, as the Apple wrapper, this one also has compatibility with Versal AI SDK. So we can freely use it as a replacement. If you write your code, you can just drop in, replace the provider because it has the same API. The last one for now, because we are foreseeing more in the future, very near future, library from this React Native AI ecosystem is a wrapper around llama.rn. This is a library that actually wraps llama.cpp, and there's a chain of dependencies here, which is a C++ implementation for running inference of models in the GGUF format, which is General GPT Unified Format. The models are stored on device. The acceleration is Metal for iOS, a Hexagon NPU, which is another SDK for neural processing units on Android only. And of course, this library as well has compatibility with Versal AI SDK. And now I would like to move to the last question. Last question, which is was ist wichtig for the developer. So now we will look at the same things, but from the developer's perspective. So the first one is framework compatibility. Which models will even work for me? And the answer is, you need to take a look at the compatibility matters, because usually you will want to reuse a ready model that's probably on Hugging Face. You have found that you want to incorporate into your application, and it may turn out that the process is complex or even unsupported for the library. As I said, there are various formats there, but also some of these libraries come with converters. For instance, MLC LLM has converters, I believe, from TensorFlow and Torch that allow you to convert the models to their formats. I think it's similar for ExecuTorch as well, and for ONNX, definitely for ONNX. It has a pretty wide range of support for other formats. Another matter is, resource usage. So is the device even capable of running the model? So if you run on a flagship, then of course it will run smoothly. But ask yourself the question, if you have a user who doesn't own a flagship, maybe an older device, will it run just as good, just as well on their device? And the solution is to actually, for instance, utilize Vulkan on OpenCL to pull in from its API information about the device. Most of the libraries of the APIs have something called compute capability, or maybe it's called somehow similar, which is usually a number that describes on a fixed scale the capability. For instance, I don't know, 9 out of 10 would mean that it's a flagship likely. And if you detect that the device is a low-end device, then you could, for instance, use a smaller model, the same llama, but for instance, with a reduced number of parameters, so that the user doesn't have to wait forever, or maybe the user won't even be able to run inference of this model on their device. Another thing that you can keep in mind is optimizations, because you can still run very large models, even on low-end devices, but only if you do some of the optimizations. And as I already mentioned a bit, some of the libraries already account for that. They have compile-time optimizations, such as MLC-LLM, that include operator fusing, so I already spoke about that, memory layout optimizations, so arranging the memory so that the specific operations, implementations for a specific platform technology are more efficient, like, for instance, in the case study that I mentioned to you, it may all positively impact the inference time. And also, there's a huge technique which is very important here, that is quantization. So, quantization is a technique that actually allows you to reduce the memory, and it's just as simple as this, what you can see here. So, it's nothing big. It enables you basically to run the models faster on devices with limited resources by applying a reversible mathematical operations on the weights. So if you have a matrix of weights, you can quantize them, for instance, from a floating point to an integer, and then you can, before inference time, actually dequantize them, and you get an approximation of this matrix. So this is something like lossy compression. And this is a big technique that allows you to save pretty much. And the finishing item I noted here is a common API for all the models. So if it did exist and all of the libraries would use it, it would be perfect. For now, they don't, but for instance, the one from the React Native AI ecosystem do. And this example here is a hello world from the AI SDK. So firstly, we have an import of the OpenAI provider. Above it, we of course have an import from the AI SDK. So this is something purely not React Native related. This is, for instance, for a server or for a web application, whatever. And then we instantiate the OpenAI client instance. So actually, this is not a model. This is a proxy that's is compatible with the AI SDK interface, but actually proxies all the calls to an API of OpenAI in this case. And this allows you to actually utilize OpenAI API with AI SDK here. And what if we could just have a drop-in replacement like this? For instance, import from this React Native AI/Apple package, and just replace this OpenAI connector instance here with an instance of the local model. And you can, because these libraries do conform to this interface. So this is as simple as this. For other providers, it may be a bit more complicated, but it's only a matter of downloading and preparing the model that is custom API. All the rest is still handled by the AI SDK. So for instance, here we import the MLC provider. Then we select the model, we download it. This may take a few seconds because it needs to download the actual file. If it's downloaded, it's already cached on the disk, so this will be almost instantaneous. And then you call model prepare. So this is an initialization phase, and that's it. Because other than that, you just pass it to generate text, and you have another provider, which actually is not always provisioned but a custom one, and it's working. And one of the implied benefits actually, is compatibility with other tools that are compatible with the Versal SDK. For instance, it includes a DevTools package, which for now is compatible only with the cloud, but this of course may change in the future. And the AI SDK also integrates with OpenTelemetry, which is, you may know it, which is a standard for performance tracing, not related to AI or React Native at all. We created a package that's called @React Native AI/DevTools, which provides an OpenTelemetry exporter. So this is a sink for the traces, the entity that you pass all the traces to export them to some server. It actually doesn't send them to the server. It pipes them to Rosenite, which is another tool that we built, and it provides React Native DevTools tabs that are customizable and extensible. And you can see them in the slide. With its help, you can easily trace everything that the AI SDK reports. So any tool call, any text generation, any streaming, with all the details, parameters, metrics. So this is very powerful for debugging what's going on inside your application, and it's agnostic as to the actual implementation of the provider used. And lastly, I wanted to thank you for your attention and hope that I am leaving you now with a valuable overview of the benefits, the options, and use case-related decision factors that your potential solutions may consume. Thank you and cheers.